Oh yeah, you also need to write down another example.
You said no. No, that's it. You said
No, it's not
you said
over.
it's over. You had your chance.
No, that's like the dialectal.
Why weren't you here third hour? Oh, you're a bad boy now? What? You're skipping school
Get
now?
out of here. You're on
Okay, that doesn't count for anything.
It doesn't?
I haven't gone one semester in high school without being on credit review. Because I don't like going to class.
It's a goal.
It's not a goal.
Same.
It's not.
Same.
I don't like.
Join the whole I can't.
How do you get on credit review for first and fifth hour, but not the rest of your class? Like, I don't understand.
I'm pretty sure they don't get it either. Are you gonna show up for your graduation ceremony?
Honestly, I don't want to. I told my mom, I don't want to go to my
I'll tell you my receipt because like
She's like, oh, you
we're gonna overhear
No,
me.
No, I know. I just grab it and be like, I'm
No, you have to show up on the freaking.
yeah, if I go, I'll grab it. I don't want to sit there full bored.
Where's voice memo?
What the hell is Marco you?
I'm Mr. Rogers.
I don't like.
Are you really
I don't like this activity.
Everyone's like, they come?
I'm not gonna break your phone.
It's gonna be too quiet.
Flavor.
I need that iPad. They're not slaves. They're indentured servants.
They're what?
They're indentured.
Hey, did you see that? I don't even remember. Hey.
So it's gonna stay like this.
On the whiteboard. Oh, but what if they start going off and he puts it away? That's why you should put it up on the whiteboard.
Wow, look at first hour.
Good afternoon, Mr. Burrow.
Good afternoon. Yes, it is afternoon, isn't
Did
it?
you see my bell on the door?
Shut up.
They see your what?
Hey, canned food? When?
Oh, I don't know.
Yeah. Not sure if it's like, as you don't want to touch the door handle. Gotcha.
I know it don't take that long time to shoot.
Howdy.
That was an awkward high five.
It was really awkward. It was an awkward high five. We'll work on it. Okay.
We'll work on it.
Yeah, because I need work on my high five.
Yes.
Yeah.
You talk a little bit. How do I say
Was eating lunch was enough for you? You need like, is it the after lunch snack? Slave labor for the snack. Slave labor for the snack.
I was in Europe.
Paper on the wall. Okay.
I have a video.
Then don't throw it away. Take it back to your desk. Jeez, oh,
I need
man.
to send a video. I tried to
Oh, yeah.
it's not here.
Who's skipping?
But it's not like it's not.
Let's see here. Biggs is still skipping. Emily is skipping. Oh, okay. Fun for her. Grace is skipping. All right.
So, who's learning the voice?
Sure.
Hey, if you'll fish, I will. Oh, wow. So far away.
All right. Okay. Welcome back. This is a long day, hasn't it been? Yes, it has. Tomorrow's gonna be worse.
Why?
Why? Tuesday, tired Tuesday. Okay,
I
but
thought you meant like physics class.
no, the Tuesday after vacation is worse. I mean, Monday's like, okay, cool, kind of excited to be back. And it's got a long day. Tuesday, like, going, oh my god.
Excited? No. We got math class.
You had a math test, a macro quiz today?
No, tomorrow.
Oh, that's okay. That's mean if they gave you that stuff today.
We got government today.
You have government test today.
I have a golf class today.
Man.
What is one of those times real high?
I got 2 in a row.
Jeez, oh Pete's.
You do like one of those.
All right. But we do have 3 weeks until next vacation.
Yeah, I got 1 week.
I'm thinking 2 tests within that time. One's by the end of the week. Remember that?
How about no?
Wait, what?
Okay. All right. Then we're on vacation. We come back for 2 days, and then yay, 2 days.
Yeah, why
January
wait?
2nd. I don't know why. Don't ask me why we're coming back January 2nd. I don't like it either.
Wait, isn't this break longer? What day do we get out?
20th. Yes.
What day of 20th?
I know. That. Don't worry. That'll be next year.
Oh, we'll be out, so
Whatever.
I'll be pushing today.
Okay. All right. So really take a look at things. We have about, say, 15 school days this month. 2, the following week of a full week of school, so that's another 5. And the following week we have 2, and then it's exams. So we have 15 within this month and another 9 within next month. That's 24 school days until the end of the semester.
Let's go.
Yeah,
Okay? All right, so this end of the semester is going to be coming up quick, that's for sure. All right. Huh? Get over yourself about no exam.
How's the exam?
Okay, we'll talk about exams later on. All right. As in this, if we do take a look at your stats, you guys are definitely well in the lead as far as that goes for bringing cans. So good job to those people who brought in cans. Yes, ma'am.
I have a question.
Yes.
Can I spread out my cans?
Absolutely.
Like 10 one day and then
For sure, no problem. Absolutely. You don't have to bring in all 10, all 50 at once, or however many you want to bring in.
because it's heavy.
I understand that. Absolutely. We had people like drag. I think people like grab people from this hour, like grab people from the hall. Say, hey, here, I'll grab cans in. They were doing it. Yes.
Since Dua isn't here, do you mind if I get cans for her and you put that extra bit in?
I'm fine with that. I'm good with that. No problem. Okay. Good. When's the canned food drive in?
December 9th.
December 9th, which is when? Next Monday. You got it. So still plenty of time to go ahead and bring that stuff in. All right. We'll have a good start here. Okay? If you want to bring a wheelbarrow with hundreds of cans, go for it. No.
I like that idea.
I'm obligated to give you guys a midterm.
You don't
Easy.
have
It's
to.
like,
It's like it's Mr. Bound to go. I can put you.
Okay. All right. Do you guys remember what we were talking about before Thanksgiving, though? Go around the circle, right? Specifically, what going around the circle? Not the rubber on the stopwatch. Car going around the circle drive, exactly. We did this thing right here. All right. We did this before Thanksgiving break. Okay, the car going around the circle drive. You guys decided to do it. Either front view or back view. Okay, those are the forces acting on it. Those are the equations we go for. We're trying to find velocity, and there's the equation for velocity, right here. Okay, and before we began this, I asked you guys what information do you guys think we need to know, and you guys told me the coefficient of friction between the ground and the tires. Yes? You guys told me you probably need to know the radius of the curvature. Good. You guys also told me we need to know the mass of the car. Okay, those things you guys told me. If we need any more, we'll come back to it. Did we need to know all those things?
No.
What did we need to know?
No.
Mass the car. We're making a lot of assumptions here. Kind of go along with this, but based upon this, all we need to know is the coefficient of friction, gravity, and the radius of curvature. Right?
Yes, sir.
We already know gravity.
Yeah.
What's the coefficient of friction?
1.
Why 1? Rubber on
Dry concrete.
dry concrete. We made the assumption as rubber on dry concrete. Rubber. What's made of rubber? Tires. Dry concrete, what you're driving on. So it makes sense as far as that coefficient of friction, right? What about the radius of curvature? But how can we find that radius? Google Maps? Okay, Google Maps.
That's just.
Yeah. It actually used to be a full circle until they put the PAC on it.
That's a thing.
Okay? Before we had the PAC, this actually did come right through here, so it was a full circle. So the PAC, yes, that's an addition. Okay? The weight room, that's an addition to the building. The fitness room, that's an addition to the building. The new auxiliary gym is an addition. The old auxiliary gym, that was also an addition to the building. Okay, so the gym, and the pool were part of the original design of the building. Okay? How can we find the radius of curvature? Huh? What tool?
I don't know, but like a little draggy.
A little draggy thing.
Like,
Yeah.
put it on the bottom drag.
Doesn't it? Yeah, it tells you how far apart. In the bottom right. The bottom right.
Bottom right?
Yeah.
This thing right here? Well, yeah, that's a scale.
Yeah.
Oh, you have to do that.
You measure the scale, measure how this
Yeah.
amount of that scale.
So we have to measure the scale,
Yeah.
and then measure some with this.
Yeah.
Okay. All right. So here I'm gonna measure the scale. Make sure you guys write this stuff down. So this says 200 feet. So if I go from here to here, that's equal to 200 feet.
Yeah.
.30 centimeters.
That's what 200 is.
Yep. 13.30 centimeters, that's equal to 200 feet. Okay? Now what?
Measure from the center. You said something about the point in the side.
It's not directly in the center.
Yeah, I said it's close to center, but not the center.
So shouldn't we just measure the diameter? Because I know.
Should we measure the diameter and cut it in half?
Yeah.
How do I measure diameter?
Longest distance.
Longest distance around?
Well, it's not like any circle, so I don't really. From one outside, a straight line that passes through the center of the circle. From one
Where's the center?
two
lines, and where they just cross.
Draw two lines where they cross?
No.
It should be.
No.
Yes, yes.
Two diameters.
Two diameters.
Where two diameters cross, right? Well, how do I draw a diameter?
It's from one end to another end. No.
No, that's, I think it'd be.
If it's a full circle, but this isn't a full circle.
Well, if we take in consideration just this part of it, if I kind of ignore this part right here, okay, so if we do some sort of measurement within this part right here, would that be good enough? Okay,
Oh, you can get a protractor and measure 180 degrees from one end, which would give you like directly on the other side of the circle.
is that the same thing as just drawing a line across?
Yeah, we would figure out like so that you don't draw a line like
So wait.
like if you drew it high enough up, it would be like small.
No.
So that's my understanding. How can I figure out the radius of curvature for this?
Wait, do we know the circumference? Do we?
I have no idea what the circumference is. Yes?
So like take the meter stick and move it down, like see where it's just the widest, I guess.
Find out where it's the widest?
Yeah.
If I find out where it's the widest, would that give me the diameter?
Yeah. I don't know.
Right on to high school. No, put it. What the hell do you do?
That's what I'm trying to do. How do I?
Put it under the high school. Oh, good job.
What?
Alright, so like start up higher and then like okay, yeah, and move it down slowly and see like look how wide it is there. And then it'll like it'll keep getting bigger and bigger and then it'll reach a point and then it'll start to get smaller and smaller. And that's just
So I'm not sure exactly what I'm looking for as far as.
biggest
looking for like a big number.
biggest measurement that comes up there.
Well, all these are bigger numbers than over here.
The biggest difference from the
Oh, the biggest difference.
yes.
Okay, gotcha. The biggest difference. Don't you hate it when I play dumb?
Yeah.
You will.
Or what I could do is just have a point fixed right here and go like this.
Right.
I know I'm right.
Yeah, I'm on that new 2020. I'm like 30.
$52.2 centimeters. 52.2 centimeters.
That's the diameter.
That'd be the diameter. 52.2 centimeters. That's the diameter.
Cut that in half. Just 26.
Okay. So now we know the diameter. 52.2 centimeters. 13.30, is that correct?
Yeah.
Okay. 13.30 centimeters is equal to 200 feet. So based upon this information, you guys should tell me approximately what the radius is.
26.1.
In feet?
Oh, feet in feet or something?
Feet? Centimeters?
Yeah.
What's the standard unit which we measure things in here? Meters.
Let's just guess.
No guessing.
Actually, I don't know where to start. I don't know.
I got 119.62 meters.
Okay, now we have 119.62 meters.
So I got
Trying to get the same thing. So far I've heard from 2 people.
So I basically what I did was like, I converted that into our scale. So I multiplied it by 3. I just did a, conventional analysis. Multiplying each of 200 divided by 13.47. So once I got that, I have 392.48. And I put that into the opposite. I got 119.62 meters for the radius.
$253? 254?
Wait for what?
Let's focus on just finding the radius here. So far I've heard 3 people.
I agree with you.
With what?
I got 119.6. Yeah. So you're saying the radius is greater than the diameter?
No.
No. He's right. I told you the diameter.
Oh, okay.
So that's the diameter?
Yeah.
Okay.
So it's center, right? Yeah.
Measure 15.2 centimeters. Yeah. So it can't be. It's 119. I know. Yeah. I thought you were talking about. No, I thought you were still talking about centimeters. I thought you were talking about centimeters.
Diameter.
I did. How much you take that shirt off? I wanted that. Sorry.
So I had
239.
Diameter.
I got 119. 60.
We're not at the challenging part yet. Oh Lord. 130.82. Was it? 119.6?
Yeah.
Hey,
So what again for the radius? 119.6 meters? Okay. First hour got right around 118. Third hour got right around 118. Last hour got right around 115. You guys got right around 118. 119. Okay, so it sounds like we're all kind of you guys all class within the ballpark of each other. Okay, good. So, do we count sig figs as of right now?
No.
No, we're not at the very end yet. So, I'm just going to put approximately. 119 point what?
162.
62 is about 120. Just for approximate. Do not use this number for calculations though. Okay? So radius of curvature is about 120 meters. Now finally get the radius of curvature. Now you have enough information to figure out how fast you can go around the circle drive. Theoretically. Don't try it. Go ahead, punch it up. Huh? You did it on Tuesday? Are you sure?
I did it at the crash show. It was pretty
I highly doubt you did at the craft show. Highly doubt it.
scared of.
I got 134.
Unless you were handicapped.
I have 34.29. So we do about 34 miles an hour. I'm sorry, 34.5. It's 30.
Is this the final answer?
No, sir. It is not.
Are you finding velocity?
Yes.
No, finding
Are you trying to find velocity here?
Yes.
So this would be your final answer?
No.
Yes.
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 Yes? So therefore, what do I want? Sig figs and
Units.
units.
34.2. No, it's 34 meters per second. No, it's 34. There's only 260. Because 120 is only 260.
That's the rounded estimate.
You can't. And gravity's a constant. Okay, I'm sorry. Okay. And it's still 260. 1.0 is 260. Oh my God. So all of them are no numbers. Because no gravity is a constant.
That's why. Like, we're plotting our final answer.
Oh, wait, no, we would just, okay, it looks like it's a 1.0.
Is 1.0 constant?
Is 1.0 constant? What is that?
Oh, okay.
Coefficient of friction between what things?
Rubber and dry.
Rubber and dry concrete. Is it always that for rubber and dry concrete? So is that measured value or is that calculated, or is that a calculated value? Calculated value, right? Okay, but is it always like that?
Yeah.
Yeah, so therefore it's 1.0, is that a constant?
Yeah.
Do you count that towards sig figs? No.
So it's 260.
So how many sig figs should your answer have?
3.
Why 3?
Because you put 3 somethings for what you meant.
When I measured the 52.2. Okay, so therefore your answer is how many sig figs? 3. So the answer is 34.3 meters per second. 34.3 meters per second. Okay, very good. That's consistent with the other hours.
Let's try.
Now, 34.3 meters per second. That probably has no meaning to you.
No.
It's not miles per hour. We're more familiar with miles per hour. So go ahead and convert that to miles per hour.
Oh,
Okay.
no.
76. That's a challenge.
No, it's not a challenge. I am not challenging you to do this.
I think you are, Mr. Brown.
Yes, it is highway speeds.
76.7 miles per hour.
About 76.7 miles per hour. About 77 miles per hour. Okay. So about 70 miles per hour supposedly is how fast you go around the circuit drive before your car starts sliding.
Hey, you can control this grip. That's cool.
However, again, do not do this. Many blind corners as we go around through here.
Well, I asked UCS to shut down the school for a day first.
No. But again, we've made a lot of assumptions.
Flat surface. 77.0.
Huh?
Flat surface.
That's a flat surface. Is a circle drive really a flat surface?
How do we know?
No.
We can't know.
Okay? It's kind of an angle, right? Angled how?
It's like
In the
Yeah, inward. No. The farther away you get from the school, the lower.
The sewers and drains?
Yeah.
Does a circle drive have drains in it? Where are those drains located? In the middle. So on the inner side, closer to school, it's banked one way, away from the school. But on the outside, it's banked toward the school. It's like a V. Okay? So when I did the measurement, I measured from the very center of the circle drive. So basically, once that tire is on the outside bank, once the tire is on the inside bank, therefore the car is all nice and flat. Okay?
So we can try it now, is what you're saying.
No. What other assumptions are we making, or what other things are we not including here? Yes?
The friction from the rubber and the road.
Friction from the rubber and the road, right? Okay, so what does that depend on? Your tires. Are these tires brand new? Are they worn or things like that? Does that matter? Absolutely. Also, it says on dry concrete. Is the circle drive actually made out of concrete? No, it's asphalt. Is that a different substance? Absolutely. Okay? It is a completely different substance. It's actually an oil-based substance. Okay? So sometimes that oil will kind of leach out on it, make it possibly slicker in sometimes. But also the sun is really beating on it, makes it stickier sometimes. So that coefficient of friction can vary.
Faster if it's stickier.
Could you possibly go faster if it's stickier? Absolutely. Okay? What other assumption do we make? What about the car? It's not going to flip over. So there's some cars that have more of a tendency to flip over than others. Which kind of cars have more of a tendency to flip over though? Taller ones, exactly. SUVs, trucks, and things like that have more of a tendency to flip over. Okay, because we call that the center of gravity is higher off the ground. So for all these different reasons, do not do this. This is all theoretical.
We're gonna like calculate like each one of our cars. how fast-
We need to get the gators from the shed. Let's try that.
It doesn't go anywhere near that. Okay? The gator. The little golf cart.
Oh.
Okay? All right. Now, so we can't, I don't want you to do this. Please, please, please do not do this. I can't stress enough. This right here is all theoretical. But there's one major thing that we did not take in consideration. You guys didn't name it, actually. It's about how the driveway is designed itself. It's designed so it's on a bank, right, for the drainage. Okay? And if actually on the inside edge, closer to school, you actually banked away from the school.
Yeah.
Or if you're on the outside edge, you're actually banked toward the school. Think about roads around here, highways, and that when you go around turns. How is it actually turned? How is it actually banked? Is it always away, or is it always toward? We say bank toward. Let's say, for example, this right here is the center of the circle. This is banked toward the center. This is banked away from the center. Toward the center. Roads are typically banked toward the center. Okay, for safety reasons. Yes, ma'am. Go ahead. So I want to take a look at this now from a new point of view. Actually, what happens if we're actually driving along the banked edge of it? Okay, so with this, I want to draw the situation that goes along with this. So, from the top point of view, that's a horrible circle. A little bit better. Okay, so this is from a top point of view. This is our circle drive. And let's say your car is right through here, and based upon this point of view, we go around the circle drive in this direction. Okay? And we have that radius of curvature. All right? We cannot see the bank from this point of view. We did not want to draw a free body diagram from this point of view. We want to draw a free body diagram from which point of view? Front or not the side, front or back point of view. Let's say we're actually standing right here, taking a look at it. So which point of view are we taking a look at from, the front or the back? The back. Okay? And from that point of view, we see the road is actually tilted like this, where this right here is the outside edge of the circle, and this right here would be the inside edge of the circle. So therefore, just for simplicity's sake, the car looks like that. Or a tire. How's that? Make sense? Okay. And therefore this thing is now at an angle. Okay? Got it? So from here, we still know our coefficient of friction. We still know the radius of curvature. And now we know angle. which this thing is banked. And based upon that new piece of information, I still want to find out how fast can we supposedly go, theoretically go, around the circle drive. Okay? What do we need to do? Force diagram?
Yes.
Free body diagram?
Yeah.
Okay, so what do I draw? Car and tilt. Good. We still draw all the objects as shown in the situation. So we're going to draw our car that's on the tilt. Okay. What forces are acting on it? Gravity. Which way does gravity act?
Straight down.
Straight down. Good. No, is there a normal force? Which way is normal force going to act? Perpendicular to the surface, right?
Yeah.
So up, up and to the right. Is there friction force? Yes. Which way is friction force acting? Which way does friction force always act? Opposite direction of intended motion. So as this thing is going around the circle drive, which way does this thing want to slide? Towards is it toward the outside circle? And where is the outside the circle in this case? To the left. So therefore, which way is friction force acting? Directly to the right?
No. Down to the right. Parallel.
Parallel to the surface, still down and to the right. Very good. Anything else in contact with it? Yes or no?
No.
Any other fields acting with it? No? So these are the forces that are present. Aren't these the same forces that were present in the last one?
Yeah.
Absolutely, makes sense. And now, what'd you say?
Change our label our axes so they can change.
Do we are we going to tilt our axes?
Yes.
Okay, what is the rule for tilting axes? What's the rule for tilting axes? Nice and loud, Jaden, because you're the only one that reached for it.
Aligned with direction of intended.
Align one axis up with the direction of intended acceleration. Is this thing accelerating?
Yes.
What kind of acceleration is it? Centripetal. Which way does centripetal acceleration always act? Towards the center of the circle. So, from this point of view, right here, which way is the center of the circle? To the right? Is it directly to the right?
Down.
Parallel with the surface.
Or is it down to the right, parallel to the surface?
Down to the right.
Down to the right? So if you're saying that, that means go around a circle like this. Are we going around a circle like this? No. How are we going around the circle? Like this, aren't we? So which way is the center of the circle? To the right. Directly to the right? Yes, directly to the right. So if the acceleration is directly to the right, is to the right on our standard axes? Yes. So therefore, are we going to tilt our axes? No. We're not going to tilt our axes in this case. We tilted before when the thing was sliding up and down the ramp. But now, because this thing is going around the circle, when we line up the direction of intended acceleration, to the right, standard axes. So because that, what do we need to do the free body diagram? Components for what? Normal and friction force. Very good. So let's go ahead and draw those in. Describe friction force in 2 words.
Right down.
Right down?
Yes.
Describe normal force in 2 words.
Upright.
Upright?
Yeah.
Okay, good. Now what? Before we, what are we going to label? Before we label components, we need the angle. Where is it? and y. What's your proof?
We're gonna do this. Alex, you want to demonstrate?
You know where the friction one is? Where's friction at?
It's like.
Where?
Like.
Left, upright, or down
Okay, so like, it's.
What's this angle?
right?
90.
90. So either this one
That one.
or this one?
It's the left.
This one?
Yeah.
Okay, so Alex is saying it's this one. Why?
Because, if you go to the other one, like the last one, the other, the opposite of that is theta, is theta,
Why is this theta?
because that's where the surface is tilted on.
It's what's tilted off of? Doesn't friction go along the surface?
Yeah.
So doesn't this right here basically the same thing as this right here?
Yeah.
Yes? Right here, so this is theta, this right here is theta? Yes? Alternate interior angles making this theta? Yes, good. Good. Everyone needs to know how to make sure they know how to find these angles. Okay, that takes care of friction force. What about normal force? Alex?
Well, where theta is on the friction force one, the actual normal force, not the component that, and the friction force are perpendicular. So then that's 90.
Okay, so normal force and friction force, those are perpendicular to each other. Is that correct? Yes? So this right here is 90 degrees.
So then the opposite of theta is 90 minus theta.
So this is 90 minus theta?
Yeah.
So this right here is 90 and this is theta, this is 90 minus theta? Yes? Okay?
And so then the opposite of that, the normal force, that is theta.
So this is theta? So why is this theta?
Because that component of normal force and that component of friction force are
What's the orientation of this? Up and down. What's the orientation of this? Left and right. Up and down, left and right are perpendicular to each other. So this right here is 90 degrees, right? If this is 90 minus theta, that means this right here is theta. Good. Got it? Label the components now. Now that we know where theta is in each of those, now you can label the components. Is the free body diagram done? Yes?
Yes.
Okay, what's next? Equations. Write the equations down to go with it. My equations up here are not complete.
First one would be MAC, right?
Would the first one be MAC?
Yes.
Why?
It's like going around the circles.
It's going around, is it going around the horizontal circle?
Yeah.
Act direction, correct? So it's centripetal. Well, which way does the centripetal acceleration always act? Towards the center of the circle. Not to the right, it always acts toward the center of the circle. And from this point of view, which way is the center of the circle? To the right, making it positive. Very good. Yes, sir. Is y acceleration 0? Is it accelerating up and down? Speeding up, slowing down, changing direction, going around the circle vertically? No? Good. Good. In addition, what else should we write down? Friction force is fun, absolutely. We have friction force, automatically write it down. What other equations should we automatically write down as now? AC equals B squared over R. If centripetal acceleration is involved, automatically write that down. Friction force is involved, automatically write the fun equation. Okay? What would be the next step? Unknowns. Go ahead and do your underlining for the unknowns.
Do we still know the mass requirement?
So what are we hoping? What are we hoping about mass? It doesn't matter, it's going to cancel each other out. So we're going to worry about the mass as right now. No. So how many unknowns do we have?
4.
How many?
4.
Not hearing a lot of people here.
4.
4?
4 different.
4 different ones?
Yes.
Ben? Are we counting AC as an unknown? Yeah. How many unknowns?
4.
How many equations do we have? 4. So therefore we have enough to solve for, right? Okay. What are we looking for on the overall? Velocity, which is right here. But in order to find velocity, what do we need to have? AC. So where else is AC? Right here. In order to find AC, what do we need to know? Friction force and normal. Okay? So in order to find friction force, what do we need to find? Normal. In order to find normal, we need to find friction force.
So we just don't do it.
No, we can do it. Question is how? Could we possibly do some substitutions?
Yeah.
Absolutely. What would you substitute?
No, substitute.
I wouldn't substitute normal force. What would I substitute friction force with? This right here. I would take this right here, mu times normal, and plug in for friction force here and here. And when I plug in here, we only have one unknown left. And therefore we can solve for normal. And then take and plug it into here, right? So that's what I would now do. Take this friction force as fun equation, plug it into both these two equations anywhere you see friction force. In addition, I was also do the same thing with AC. Substitute AC and make it V squared over R. Got it? Make those substitutions. And I'll substitute weight, make that mass times gravity. So now it should look like this. You've made some substitutions, right?
Yeah.
Go back through and find out your unknowns again. How many unknowns do you have? Two in two equations. What are we trying to look for over the overall? Velocity. But in order to find velocity, we need to find normal. Normal is here, normal is here. Right? So we need to find normal force. Normal's here and normal's here. How many unknowns do we have in this equation? One. Therefore, can we find normal force here? And take and plug into here? How would we find normal force here? Would you factor, n is common here and here, therefore would you factor it out? Take mg, put it on the other side, factor out the n and then solve for normal force? Then once you know that, plug into here? Yes? Now, before I turn you guys loose to do it, n is common these two things, right? I'd factor out the n. That way you plug the normal force into just one spot as opposed to two. It'll make it easier. Got it? Do it. Solve it. Come up with the final equation for velocity. Go ahead and do that. Yes, sir.
Will we factor out that m, does that mg, we factor that out too?
Nope. I put mg to the other side
Okay.
and then factor out the n. The equation got a whole lot more complicated, didn't it?
Static,
Yeah. Because that's normal force. So I substitute this in for here. But it looks a whole lot more complicated, doesn't it? Okay. Just because adding this little angle to it changes things. All right? Now, next question is, how much is this circle drive actually banked? And what angle is it actually banked at? What? Huh? Just drew three angles here. This right here, that's a 10-degree angle. From here to here, that's 20. And from here to here, that's 30. 30 is pretty steep, isn't it? Yeah, it's not 30. Okay? 10's is just a little bit, right? Okay? So if the angle was 10, because it's not banked that much. In some locations, more than other locations. But 10, let's say it's constantly 10 across, all the way around. Angle is 10. How fast can you drive around the circle drive now? You know everything else. The only thing you needed to wait for me was now the angle, theta. So calculate it. So yeah, we're going to call the angle 10, 10.0. Make it 10.0. Anyone get anything?
Oh, you chose that.
40.9
Meters per second.
meters per second.
It's 91 point.
Which one? 91 miles an hour?
Yeah.
So you were at 77 miles per hour. Now you're at 91 miles per hour. So just by that little 10-degree angle, we're able to go 14 miles an hour faster. Some cars out there probably can't go 91 miles per hour.
Let's go slightly the other side.
Let's tilt the other way.